Well, hello there. So this is going to be the second part of Module 1B, and we're going to look into a little more detail on Kirchhoff's laws, including the voltage divider, current divider, and equivalent resistor circuits. So the first concept we'll get to with Kirchhoff's laws is these equivalent circuits. Parallel and series resistors are the main ones. But the idea of an equivalent circuit is something that will run through our class, and so it's taking a look at what that means. So the idea is we have two circuits here, original circuit segment and rest of the circuit, connected with two wires. And so the equivalent circuit means that if we take away this original one and replace it with an equivalent one, then from the point of view of the rest of the circuit, it looks the same. So any voltages or currents flowing on these wires are going to look the same from the rest of the circuit. It doesn't necessarily mean that energy is used the same way on the equivalent side, because you could have wasted energy that's just not doing anything. But this is the model when we have a circuit with two leads going out, we can make an equivalent circuit. So the first equivalent is resistors in series, and you may have already seen this. This is a common result, but it's worth looking at this from the point of view of Kirchhoff's voltage law. So Kirchhoff's voltage law, remember, says that the voltages as we go around a loop must sum to zero, and our sign convention is we go clockwise in a circle, and as we hit the polarity of a terminal, we add or subtract it based on which sign we hit. So we'll go clockwise, so we're going to go up through Vs, so we're going to subtract Vs, and then add V1, add V2, add V3, add V4, add V5, and that will sum to zero. So negative and then positive all the rest. So if we rearrange things, we get this KVL equation by going around the loop. Then we use Ohm's law. Remember Ohm's law, V equals IR, as long as I goes from plus to minus. And so we do have I going clockwise, and all of the resistors have the polarities going clockwise too. So it should work out that V1 equals IS times R1, V2 equals IS times R2, and so forth. So we get this second equation down here. So this is a combination of Ohm's law and Kirchhoff's voltage law. And those Kirchhoff's law and Ohm's law are really the key to solving most circuits. And then we're just factoring some things out. So we get this Vs equals this big sum of all the resistors times Is. And if we want that to be an equivalent circuit, we would draw it like this. We have two wires here, so we cut them, and this is an equivalent circuit with just a single resistor, equivalent resistor. And if these are going to match, then our equivalent has to match up with this sum. And that way we get the same circuit. So R equivalent equals R1 plus R2 plus R3 plus R4 plus R5. These are in series. So the big takeaway is that resistors in series add, which you may have already seen before. But it's also a really good application of using Kirchhoff's voltage law in combination with Ohm's law to solve for a circuit. We could find Is given all the parts of the circuit, the voltage and the resistors. We could solve for that. And then once we know Is, we could solve for the individual voltages. So this is a really powerful combination of laws. The other thing that comes up with series resistors is the voltage divider. This is two resistors in series connected to a voltage source. And so the analysis is exactly the same as we did for the equivalent resistance. Kirchhoff's voltage law, Vs equals V1 plus V2. Here V1 would be, it's not even shown, it would be right here, plus minus V2. And then Ohm's law for V1 and V2. And if we combine these together with the goal of finding V2, you could first find Is by plugging in these two up here and solve for Is, and then plug in Is here and find V2. Anyway, combining those equations gives you this answer. So V2, R2 over R1 plus R2 times Vs. So V2 is proportional to the source. If you double the source, you double V2, but it's reduced by the ratio of the resistors. So R2 over the sum of the two resistors. You can do the voltage divider with more resistors in series, but this is by far the most common one. We have this is a very common circuit that shows up. So it's worth keeping this equation handy, because when you see this, we can analyze it really quickly, but just knowing the voltage divider equation is useful. Sometimes I forget which resistor goes on top. It's the sum of the two on the bottom, but it's the resistor that you're measuring the voltage across. So R2 is what we're measuring across. We have a common ground with V2 and Vs, and so R2 is the resistor that goes in the numerator of this fraction. So we'll see the voltage divider a lot. It is really good for sensors. If you have a sensor that sends a voltage that's too high to measure with your data acquisition system, a voltage divider will reduce that, but still keep it proportional. So if the voltage changes on your sensor, the input voltage changes. So here's an example of a 10 volt. I don't know where you got a 10 volt Duracell, but this is 10 volts and a voltage divider. And so using the voltage divider equation, you can show that this one's going to get 6 and this is 4, and you can see Kirchhoff's voltage law, 10 equals 6 plus 4, so all of that has worked out. This is a common setup. If you have something like an Arduino, if you've ever used that Arduino microcontroller, it can only measure voltages up to 5 volts. If you put 10 volts into an Arduino, you'll burn out the chip, or at least the pin. So if you want to measure the voltage in your 12 volt battery, I at one point had a sailboat, and I put a little Wi-Fi Arduino module in, and it would send a Twitter update with my battery voltage, and I had some sensors so people pulled the hatch boards and things. This was a long time ago when the Wi-Fi in the marina changed, and I had to get rid of it. But I used this exact same kind of circuit to measure the voltage of my 12 volt battery, reducing it down to about 5 volts with a voltage divider. So if this voltage is 10, we get 4 here. So that's a nice safe voltage for my Arduino that can't measure more than 5 volts. And then as the voltage changes, as this goes to 9, this will also reduce. And if this gets bigger, this will also be bigger. So this is a nice way to have a ratio that's proportional to a voltage that's too high to measure safely. The big mistake people make with voltage dividers is sometimes people use them as a power supply. You need 5 volts to charge your phone, and you have a 12 volt battery in your car. So you think, oh, I'll do something like this, and I'll make this be 5 volts from my 12 volt car supply. The problem with that is that voltage won't be constant. You won't get a nice solid 5 volts, which is what your phone really needs. If the battery voltage changes, this will change, but also this voltage only is true if there's no current coming out of these wires. So once you add a load, you put your phone here across these wires to charge it, it's going to pull several amps through there, and that's going to change the whole circuit. So as soon as you draw any current, significant current, the voltages change and your equation's all wrong again. So in the Arduino battery sensing thing, the Arduino measurement takes very, very little current, like millionths of an amp. So for all intents and purposes, it doesn't draw any current here. But if you're providing power, if it's a power source, then obviously you need to provide current. So, so don't use a voltage divider to make a constant voltage supply. There's actually a part called a voltage regulator that costs about $1 or less, and it's got 3 wires, and you put your 12 volts in, you've got ground, and you get a nice solid 5 volts out, and it measures and adjusts and does exactly what you want. So if you're looking for power supplies, constant voltage, use a voltage regulator. If you're looking for sensors, ratio, proportional reduction of voltage, that's what the voltage divider is for. Okay, here's the typical voltage divider again, and our equation. And this is the bad idea if you're trying to charge your phone. If this is your phone modeled as a resistor because it absorbs power, once you start sending significant current through these wires, then you basically have these two resistors in parallel. So R2 becomes R2 in parallel with RL, and that changes all of this equation. It comes in two places, and so all the numbers change. And if your phone doesn't have a constant equivalent resistance, then it's a big mess. But for sensor applications, the load resistance is approximately infinity. The impedance of a multimeter is generally millions of ohms, so that's infinity to 6 decimal places anyway. So sensors, yes. Power supply, no. Okay, so we can do a similar thing with resistors in parallel that we did in series. In series, we used Kirchhoff's voltage law because we have a single loop. With resistors in parallel, we'll use Kirchhoff's current law because we basically have, there's two nodes, the top node and the bottom node, but they're the same equation because it's got the same current going in and out and in and out. You don't get different equations. So if we write Kirchhoff's current law at this top node, remember this, all this big wire on top, that's all a single node. We have IS coming in from the voltage source, and I1 and I2 and I3 going out. Remember, we have to draw the arrows with directions, and then the current going in equals the current going out. I'm missing teaching in a classroom because here's where I train you for one of the funnest things to do, and especially the echoey classrooms we have sometimes. It's always Kirchhoff's law and then it's Ohm's law. And so here's my prompt, and you can do this in your head. I say, so we do Kirchhoff's law, and I say, and now whose law is next? And you as a class, you go, Ohm. Ohm, and it sounds really good when the whole class does it, and it's probably terrible when I do it. So thanks for indulging me in my fun part of teaching. Ohm's law is always second after Kirchhoff's current law or Kirchhoff's voltage law. Here we're trying to solve for the currents, so it's V over R, and because these are in parallel, they all have the same voltage. They all have Vs. Parallel elements always have the same voltage, so we can replace I1 with this, and I2 with this, and I3 with this, combine them together to get this equation. And then if we want to make an equivalent circuit, we would replace these three resistors with a single equivalent resistor, and we'd have an equation where IS equals Vs over R equivalent. That's just basically Ohm's law. So these have to match. So 1 over R equivalent has to be, we can factor out Vs, 1 over R1 plus 1 over R2 plus 1 over R3. So while you're taking notes, fill in the extra steps here just so you see how this is done. And we get this equivalent resistor for parallel resistors that you've probably seen before again. I call it the 1 over the 1 overs because it's 1 over R1 plus 1 over R2 plus 1 over R3. That's the equivalent resistors in parallel. 1 over the 1 overs. With resistors in parallel, we can also talk about current division, where we have a current going in and then it's divided. These are in parallel, so the electrons can choose whether they want to go through this one or this one, and the amount of electrons goes proportional to how hard it is to get through these. So with a similar analysis that we did to the voltage divider, we can do a current divider, and we get these equations that look a lot like the voltage divider equations. I1 equals R2 over R1 plus R2 times IS, and so forth. These come up a lot less often than the voltage divider. I think mostly we solve for voltages more often than currents, but the analysis is very analogous, but you'll use this one hardly at all, and you'll use the voltage divider lots and lots. But we present them both. Okay, so here is a circuit analysis using the equivalent circuits idea. So the idea is we can simplify the circuit down to something we can solve by inspection if we combine resistors in a clever way. So you have to be able to spot them. This is a really good recommendation that students sometimes try to shortcut, but combine two resistors at a time. Pick obvious I know these are series or I know these are parallel, redraw the circuit, then take a look at it again. With equivalent circuits, it's hard to be methodical. You have to kind of see it. So redrawing it after you do 2 easy ones at a time, hopefully after you redraw it, you'll see the next 2 easy ones and you can keep going. So for example, in this one, these 2 resistors, R3 and R4, they're in parallel because their heads are connected up here, tails connected down here, just 2 nodes and the 2 elements. So combine those and then redraw it. So we're going to leave all the rest. Well, actually, we're not. These 2 combine to here. And then they're also doing the 2 and the 4 in series, giving us the 6. So we did 2 at once, and then we'll look at what's next. And so now we can see we've got this one and this one. They're parallel because their heads are connected to this node, tails connected to a different node, but connected together. So we can do those in parallel, and we'll get this 2 ohm. And then these 2 are in series, so we can finish it off. So can look for I1 is 24 volts divided by 10 plus 2 is our 12 ohm equivalent resistance. So we can solve for that current, and then you kind of work your way backwards, and then we can use Ohm's law and Kirchhoff's current law. So again, this is a method that works. Sometimes it's really obvious to do this, and that's the best time to use it. For a general complicated circuit, the methodical techniques of node and mesh analysis that we haven't learned yet are really more advisable because you don't have to simplify the circuit. It works on everything. You can just go ahead and apply the step-by-step. So these, you have to kind of see the picture. If it's drawn in a weird way, sometimes it's confusing, but use it when you can. It's also a good way to check things, have 2 different independent analyses. Okay, so just a little bit of stuff that this book threw into chapter 2, so we'll talk about them here. I is current and V is voltage. So IV relationships, normally I goes on the y-axis and V on the x-axis. And so each element has its own function of IV. So a constant current source, an ideal current source, has constant current, infinite range of voltage, whatever this system needs. A voltage source is the vertical line, constant voltage, and the current is whatever is demanded by the circuit. Resistors have a slope, and the slope is 1 over R because I equals V over R. There are other components. Semiconductors come into play here. The diode is an element that you'll see more in the lab than in lecture. The diode is used normally to block current from flowing in one direction. So if you're thinking of hydraulics, it's like a check valve. And the diode symbol is an arrow, so that's showing that the current can only flow down in this one. And the little whiskers here are, if you look at a diode, it has a stripe on one end, and the whiskers are the end that has the stripe. That's what I imagined before. So the arrow shows the direction. Current can only flow down. If we try to push current up through that diode, it blocks it. And it has to do with the semiconductors, but we won't go into the physics. So the circuit diagram for an ideal diode looks like this, where current can only flow in the positive direction. It's blocked in the negative direction. And that's an ideal diode that has a one-way current. An actual diode has an exponential, so this is the real diode response. And you'll actually do a circuits lab where you measure this. You'll measure current and voltage across the diode, and you should get this exponent, and you'll find the coefficients of the exponential to match so that theory matches experiment. That's the way it really works. A really common model for a diode in a circuit is to just assume, that this goes exponential, but it gets pretty steep around some constant voltage. So something like 0.7 volts is not a bad number to use. And so we assume that it just goes vertical at this forward voltage VF, maybe 0.7, something like that. Depends on the kind of diode. LEDs, the light emitting diodes, depending on the color, they have a different voltage drop. But we basically lose a little voltage across here, and it doesn't really have much other effect if it's this ideal. So if you make that assumption, this is a really common assumption, then you can go and use our things like Kirchhoff's voltage law. We just assume that's a constant voltage. If it's not, then we have a nonlinear set of equations, because this is a function we can apply, but it's not as linear, and so it makes the solution, the numerical part, harder to find. All right, so as a summary, today we have looked at resistors. This is all of chapter 2 so far. V equals IR. Kirchhoff's current law, that's key. Use that one a lot. Current in equals current out. Kirchhoff's voltage law, as we go around any loop, any closed path, the sum of the voltages has to sum to 0. Series resistors add. Parallel resistors, it's the 1 over the 1 overs. Voltage divider is definitely worth learning. Current divider, you can derive it if you need it. And that's going to do it for our chapter 2 summaries. So the next module, we will start to get into actual node and mesh analysis. Those are the step-by-step process that can solve any circuit, any resistor network to start with. But for now, you've got these tools, so we'll apply them for the homework. All right, I'll see you later.